My name is Philip Nickerson. I'm an engineer with Goshen Halibut and also with my own company, Aqua Production Systems. And I want to discuss a new product that I'm very excited about, heat pump that has been specifically designed for aquaculture applications. And when I refer to heat pumps in this presentation, our key piece of technology is a reversible water-to-water heat pump, but the same principles and the same technology is also applicable to non-reversible if you only need to heat or cool, but you want to use water-to-water technology for its efficiency advantages, and it's also applicable to air-cooled chillers. So if you need to cool water and just dump the heat into the air, everything that's discussed here will also be applicable. The same technology can be used to gain much efficiency advantages there too. So a summary of the presentation. Why do we heat and cool in aquaculture? Some challenges specific to the aquaculture industry and the application of heat pumps. What are the goals of this new heat pump technology during the design phase? And then a brief overview of the heat pump itself and some examples and stories of heat pumps at work. So why in aquaculture do we heat and cool water? Fish being cold-blooded are dramatically affected by the temperature of the water that they're in. It affects their feeding activity, their growth rates, their reproduction, whether they will or not, or how well they reproduce, how soon they reproduce. One of the key reasons that an aquaculturist will want temperature control is to have year-round optimal growth rates, or more than what the natural ambient temperatures would give, longer times of optimal growth at the water temperature that is optimal for the fish. Another reason might be to have a spawning cycle happen at a specific time, or to have multiple cycles per year, to have a continuous hatchery operation rather than seasonal. And some of the issues that would be associated with not having enough temperature control, heating or cooling capacity. Your fish will feed less, therefore they'll grow less, take longer to get them to market. Or you will be looking at purchasing more heating and cooling equipment, which results in a higher energy bill, higher maintenance costs. In some cases I've seen you have to buy more equipment to support the heating and cooling equipment, a bigger footprint. If you need to back up the system with electrical genset, that all has to be taken into account. So some of the challenges just with heating water is that it has a high heat capacity, which makes it energy intensive and therefore financially burdensome to heat water. In fact, it's about 30 times more energy to heat an equivalent weight of water than to heat mercury or gold. Traditionally, non-sustainable resources have been used for heating. Coal, oil, natural gas, propane, these all have generally rising costs, but typically unpredictable in nature. They fluctuate up and down year to year. But oil, for example, in the last 12 years has gone from 35 cents to $1.10 per liter. So something that may have made sense 12 years ago to use oil for may no longer be financially feasible. Similarly, these these methods of heating have environmental emissions associated with them that are not very desirable. ends up putting a rather ugly fossil footprint on a product that, as an industry, we're trying to promote as sustainable, perhaps even organic in some cases. So, a little different approach on the challenges is that some of the heat pump technology that you might see in other applications can be taken and applied to aquaculture, and often is done so very inefficiently. For example, somebody might take a swimming pool heat pump and try to use it to heat aquaculture water in the winter. Well, if it works at all, it will be so far out of its range that it will be operating very inefficiently because of the difference in temperatures between its intended design range and the winter temperatures. Some of the challenges for cooling, and this kind of fits under heating too initially, that most refrigeration techs and suppliers don't have a firm grasp of the aquaculture application because it's not that well known, especially land-based at this point, and vice versa. Most aquaculturists do not have a firm grasp of refrigeration, and nor should they. But somebody has to fill that gap, and so in the past 5 years, in trying to learn to bridge that gap, I've seen some of the following. Basically amounts to a plague on the industry. For example, chillers operating out of their intended range. One site I've visited had 20 chillers, couldn't reach their temperature. Did some investigation and found that 11 of them had compressors that were operating below what the manufacturer recommended. In fact, they didn't even publish any data for the range that they were being operated in. So they were being run very inefficiently. But even some of the ones that were in the intended range were operating at 50% roughly efficiency. And the method used to control chillers and applications and used to incorporate them into the aquaculture system is often done inefficiently, simply out of the knowledge gap that exists between aquaculture and refrigeration. The bottom line is 40 to 70% higher energy costs than necessary for cooling water. Being operated outside of the intended design range often results in higher maintenance costs, failed components, and in the worst cases, loss of product. Why is there so much trouble in this specific application? Well, aquaculture, especially hatcheries, have variable flow rates, variable temperatures. Bring in ambient water that could have a wide range from winter to summer. Ambient air, if we're using that as a source or sink, could change drastically. Target temperature often stays the same, but between different sites, different species, that would change as well. The environment in a hatchery is often very humid, very wet. If it's a marine environment, very salty. It is a rather harsh place for a piece of equipment that is often expected to run 24/7. The aquaculture application is equipment there is often very critical processes. A failure of the equipment could result in product loss, company loss, and as I mentioned, between different sites, different species, you really need different heat pumps. The same piece of equipment won't work at the different temperatures required. And conversely, refrigeration is a challenging application. It's not intuitive, it's not something that anyone's going to pick up overnight. even the refrigeration techs that we might call in to service the equipment are trained to install and service, not design the equipment. So even once they understand the application, they may not be able to bridge that gap. So what is the goal when we set out to bridge this gap, find some technology that could serve the aquaculture industry? Well, in most things that I do as an engineer, if not all, the goal is to get the aquaculture technicians more focused on producing fish and not have to worry about managing less than ideal water quality, water temperature events, reacting to equipment failures rather than proactively growing their fish. Another benefit of the heat pump would be to have one piece of equipment that could heat the water and cool the water, rather than the more common application of maybe oil-fired boilers to heat, air-cooled chillers to cool in the summer. Simply with the heat pump, less capital cost, less maintenance cost on one piece of equipment, less footprint required, and so on. So this heat pump would also have to be easily customizable to go from one species to another, one site to another. High efficiency is a must, and reliability is clearly something that has to be focused on in this application. So the answer we've come up with, a reversible water-to-water heat pump. And I'm quite proud to say it's a Nova Scotian product. To our knowledge, there's no equivalent product in the world with this capability to reverse, to be reversible in this application. And the only one we know of, the only heat pump we know of specifically built for aquaculture. The technology that allows this reversibility is from Wilson Titanium Products, the manufacturer. Applications engineering for the development for the application of each unit bought is by Aqua Production Systems. Current Controls provides quality components. They're the regional wholesaler of HVAC equipment. And having the aquaculture environment in mind, this heat pump was built to last, built with industrial grade materials and methods. The wetted portions that come in contact with the aquaculture water in and out are built with titanium and PVC, so no corrosion is going to happen. The electrical portions are all built to withstand the environment as well, and the compressors are often reciprocating and more durable and selected for their quality as well. So the unsurpassed efficiency, these are numbers actually measured on Wilson Titanium units that were installed on a federal site. Coefficient of performance 4 for cooling, 5 for heating. The coefficient of performance it's a measure of efficiency. In refrigeration, you can pay for, say, 1 kilowatt of electrical energy and transfer 4 to 5 kilowatts of heat energy. So rather than have an efficiency of 400% or 500%, we use the unit coefficient of performance to measure the efficiency of refrigeration equipment. And the water source was chosen as an ideal fit for aquaculture applications. Water coming in means water's leaving. So the water leaving would simply serve as a heat source for the heat pump. So here's a picture of two of the units that were built and installed at the new DFO site in St. Andrews, New Brunswick. Part of the customizability of these units is the number of barrels, the length of them, the diameter of them, and the selection of the compressors specific to the temperature and flow rate needs of the application. This is actually two units, one stacked on top of the other. So, the sustainability factor. Well, we've already covered sustainable by efficiency, but in Nova Scotia, energy has been generated by several different methods for years, primarily coal. Now a push is on for renewable sources, 17% currently in 2011, 40% by 2020. Hydro, tidal, wind, biomass is now coming online. So in Nova Scotia by 2020, anything that you plug into the wall will be 40% renewable energy. So these heat pumps have maybe 40 to 70% higher efficiency, or 40 to 70% less energy requirements, plus 40% renewable supply by Nova Scotia Power. And they could be run off of any renewable energy that might be generated on site, for example. The customization is really an important factor here. No matter what the species or the site, once the conditions are known and described, the unit can be built to match and to operate at its peak efficiency across that site's specific range, temperature range. We've been lately doing some work on VFD control of the heat pumps. This provides two things: even more efficiency, as it matches your demand it matches the heat pump's output to your specific demand, and it also gives better control rather than an on-off cycling type of control. If more precision is needed, the VFD can handle that. So some examples of units that are in operation, installed and working. Scotian Halibut has one at their site in Clark's Harbour. It was installed to replace oil-fired boilers, and by doing so, we've seen a 70% reduction in heating costs as compared with oil. And as a result of that reduction in costs, we've also seen increased heating capacity, which allowed us to send more temperature-controlled water to certain tanks and thereby increase production. These are actually broodstock tanks, and we've seen a dramatic increase in the egg production from those tanks, which translates into more product going out the door. Gidney Fisheries is actually a lobster pound, and they had a pound running on 50 horsepower worth of chilling, our competitors' chillers, and they built a brand new pound next door, and we put in a bid for 30 horsepower worth of chilling on the new pound compared to our competitors' 50. And they were installed about 2 years ago, and since then we've heard that the pound with 50 horsepower worth of chillers does not reach its temperature during the summer, and the chillers do not cycle off. They run steady 24/7. On the new pound with the Wilson Titanium 30 horsepower chillers, 30 horsepower worth of chillers, the pound reaches temperature quickly and the chillers cycle on and off as needed. So at least a 50% reduction in cooling costs there using air-cooled chillers. And St. Andrew's Biological Station in New Brunswick have built a new facility and installed 12 of the reversible water-to-water heat pumps, 3 different sizes. They also cut back their stocking and their use of the facility somewhat. So only about half the units have seen real use, but they're very happy with what they've seen there. So just to give you an idea of how applicable this technology is, if you use 10 horsepower worth of cooling equipment and operate 24/7 for 6 months a year, you're going to see a very good payback by switching or installing the Wilson Titanium technology. And similarly, if you're heating using about $3,000 per year to heat, your payback will be likely very attractive. It depends obviously on your heating method and your current efficiencies. So if you fit either criteria 1 or 2, please contact me as the applications engineer for this product, and we can discuss if it's a fit for you and what your potential savings might be, and what possible applications you might have for them. And I can only really speak for Nova Scotia on the efficiency incentives, but certainly if you are in Nova Scotia, these units may be partially covered by incentives from Efficiency Nova Scotia. So we can certainly discuss that too. If you contact me, my email was on the cover of this presentation.